Hi everybody, welcome to another episode of XR Advanced. Today we have Suma Rosenberg. He got his PhD at UNC Charlotte, and he's now assistant professor at University of Minnesota in the CS department, although he just recently arrived there from being associate director of the MXR lab at the Institute for Creative Technologies at USC. Perhaps most famous, although he's done a lot of cool things, I think it's for redirected walking. I don't know, that's one of my favorite tools. So he's going to talk to us today about illusions in virtual reality. Thank you.
Thanks very much for the introduction, Stephen.
So as he said, I just recently joined the University of Minnesota. Although I'm a newly starting tenure track assistant professor, I've been a researcher working in the VR field for over 15 years now. And over that time, I've worked on many different projects ranging from basic research to applied research to prototypes funded by the US Army and the Navy. But in addition to that, personally, I'm also a consumer of VR content. And my experiences playing VR games at home as an end user are synergistic with my interest as a researcher. Playing VR games helps me to understand the limitations and the interaction problems in the current state of the art that directly informs the research that I do in the lab. Although my wife will tell you, who is currently watching this live stream, that sometimes I take this a little too far. So I've worked on a lot of different things, but if there's one sort of central theme to my work, it's looking at these sort of universal interaction problems that apply to a broad range of different VR applications. And one of the problems that is really universal to any VR application or system is the problem of locomotion, how you move in space. And the origin of this problem should be hopefully intuitive for everyone, but here's a fun little animation to show you what happens when you're moving in a physical space, but you want to walk through a large virtual environment. Well, at some point, you're going to hit physical boundaries. You're in a room of finite size, but we don't want to be limited to a single room virtual environment. We want to be able to explore virtual cities. We want to explore large open worlds. So how do we solve this seemingly intractable conflict between the physical space that we're inhabiting while wearing these headsets and our aspirations about the virtual content we want to consume? And before I continue down this path, I just want to address the themes of the XR Advanced series. I was asked to sort of align my talk with some of these central themes, and if I had to pick one, I would say a lot of this work really touches upon the idea of optimizing the human-machine interface, particularly locomotion interfaces. But you're going to see a lot of the other themes of XR Advanced coming up through this work that I just want to highlight. One is cyber sickness is an issue that you're going to see being addressed in this work. We do a lot of studies of spatial cognition. Identifying user states and traits are another important aspect. And then even dynamic content generation you're going to see in some of the work that I'm going to present in the next hour. Okay, so let's talk more about this problem of locomotion. Now you could say, well, we know how to move around in games. People play these all the time. They sit on a couch, they have these handheld controllers, and they fly around the virtual world using the thumbsticks on the controllers. So when VR first came out in the consumer space back in like 2013-ish, the first gaming interfaces and experiences you saw looked pretty much like this. You know, that's exactly what they did. So great, you know, why do we need to deal with this physical space problem? Well, after VR started becoming popular in the public consciousness, you started to see headlines coming in the news, and these are just some of the ones that I've snipped out of recently, that look a little bit like this. Turns out that when you make people fly through a virtual world, but they're not moving physically, this is one of the things that is known to be associated with motion sickness. And so this is a huge problem for the VR community and for the public adoption of these technologies, and it's not a solved problem today. It's still acknowledged by Oculus and other HMD manufacturers as one of the major barriers for adoption of VR technologies. And if you look at the hardware sales, we can see that this is even just a couple years ago. We're shipping now VR headsets in the millions of units every quarter. And so these are out in the world. People are buying them. They have all these headsets, made everything from mobile headsets to PC, high-end PC tethered headsets. But if you look at software versus hardware sales, oh, whoops, mic popped off. this actually tells a somewhat different story about sort of the health of the VR industry. Typically, what you want to see when someone releases a new technology platform, like say a new video game console, is you buy the hardware once, and then you buy software and apps and content and you spend more money on the content than you do on the initial hardware investment. This is what allows many of the game console manufacturers to actually sell the hardware at a loss or at least break-even point, because they make it back in software. Well, I don't have the numbers for 2018 yet, but so far the trend is actually the opposite in VR, that people are spending more money on the hardware, but in terms of games and application and content, it's actually those sales have not exceeded the hardware sales. And this is a sign that the VR, at least for the entertainment space, is an underperforming industry so far. And I think that we can look at this from an entertainment perspective, but we can also look at all the serious applications of VR and how many different, in so many different domains VR can touch, that these problems that the entertainment industry is facing is actually a good sort of warning sign, or it's a good test space for us to figure out these interaction problems, hopefully solve them so they can be used for productive purposes. And to this end, institutes like the National Academy of Engineering Grand Challenges for Engineering, for their 14 Grand Challenges for Engineering in the 21st Century, enhancing virtual reality, solving these problems is one of their grand challenges. So at this point, one might ask, if you're familiar with VR, well, wait a minute, we don't have to just use gamepads and controllers to move around. Wasn't the promise of HTC Vive's wide area tracking system that we could have room scale VR? That we could put two trackers and emitters up in the corners of the room, and then we have this space that you can move around in, and you don't need to use these virtual locomotion techniques. And it turns out that yes, when we can actually physically walk, when we can move our bodies synchronized with the virtual motion, people get a lot less motion sick. And there's a lot of other cognitive benefits as well in terms of your spatial cognition and just the level of immersion. So walking is good. But after the Vive was introduced, we started to see a lot of VR blooper videos, things like this popping up on YouTube. Here's just a quick example of what you see to happen when you put these in people's homes. So this is pretty obvious, right? You know, this is the problem I talked about before with hitting walls. So we have the ability to walk, but our walking space is finite. So how can we best leverage the space that we have to allow you to walk naturally through the virtual environment so we don't have to use those nausogenic techniques like virtual locomotion technique using the controller? Now this leads me to the techniques known as redirected walking, which Stephen mentioned briefly in the introduction. For those who are unfamiliar with it, I didn't come up with redirected walking. It was first introduced in 2001 from researchers at UNC Chapel Hill. And the original paper sort of just pointed out that there's the ability that we can, properties of the human perceptual system that we can exploit to solve this engineering problem. In their original example, they showed, and you can see here in blue, a virtual world path. It was a virtual fire drill scenario where they went for this kind of figure-8 path, or sorry, zigzag path, pressing a series of buttons. But in the real world, they were just walking back between the same 2 points in the physical lab space over and over and over. So this has been a very influential paper that has spurred an entire research sub area of virtual reality, and many researchers were inspired by this work, including myself. So how did they pull this off? Well, the original redirected walking techniques that were introduced actually used 3 different type of sort of motion illusions, which we refer to as gains. The first one is called translation gain. And so the idea here is that we're actually going to scale up a component of the user's self-motion. So as the user, say, moving forward in the physical space, walking forward, we can scale up or we can scale down by a certain degree their distance in the virtual space to walk a greater or smaller compressed distance. Another slightly more complicated technique is what's known as rotation gain. And instead of this time amplifying translational velocity, what we're going to do is actually amplify the yaw rotation as they move their head. So in this example, they rotate 90 degrees in the virtual space, but that maps to a 180-degree rotation in the physical space, and then they're able to proceed and basically walk back along the path they've already taken. And then the final one is a little bit more complicated than that. It's what we call a corrective gain, and it's known as curvature gain. And what we do here is, instead of amplifying directly a component of their motion, what we do is we slowly rotate the virtual world around the user's head as a function of their forward velocity. So basically, as you move forward, you get a slight turn steering you towards one direction or the other. And what this does is you essentially unconsciously correct for it, and you walk along a curved path in the physical space, but perceive that you're walking straight. So all of the redirected walking illusions, at least the ones that I'm going to talk to specifically when I talk about redirected walking as a technique, uses these three gains basically as primitives and combines them within some sort of experience in some way in order to allow you to walk through a larger space. So here's an example of how we can actually use this to walk through pretty large spaces in a very confined area. So this is a experience we put together as the first place winner at the SIGGRAPH AR/VR contest in 2015, and when we submitted our demonstration to the contest, which was actually an environment to demonstrate some new image-based light rendering techniques being used with stock animators that are doing stop-motion animation, they said, okay, you're going to bring it and do it on stage and demonstrate it to the audience at SIGGRAPH. And then we said, well, how big is this space? You have to walk around. This is really important. You got to get up there into the objects and really get your body involved. And it was bigger than our environment was bigger than what they had. So what we did was we used redirected walking. So what you saw there was, and I'll replay that for you just a moment, is that what they're essentially doing here in this experience is walking back, again, sort of like along this zigzag path between these exhibits. Let me zoom back here. And the physical path that they're taking is basically that yellow path in the teal square. The teal rectangle there is sort of indicating what the physical space boundaries are. And we put this couch in our tracking space for no practical reason other than to give you a sense of scale, that this is basically they're walking back and forth within a space that could feasibly exist in your living room. So when used properly and in the right context and the right VR experience, redirected walking can be pretty powerful. You can use it to go through much larger spaces in relatively confined spaces if you use it the right way. So let's talk a bit about why this works at a perceptual level. One of the core mechanisms that makes this possible is known as visual dominance. And what this is basically the observation that if you have two conflicting signals being processed by your brain, what your vision is telling you about your self-motion, and what your vestibular system is telling you, liquid swirling around in your inner ear relative to gravity as you move around, vision tends to dominate over the vestibular sensation. That means you tend to believe what you see over what your body is feeling, with an asterisk, and the asterisk here is a big one. It has to be below what we call our perceptual detection thresholds, your tolerance. If you exceed that and the conflict rate grows too large, then not only will you begin to perceive the difference, it'll probably start making you sick. So one of the of course, first things that the researchers started to study with this was, how do we quantify this? What are the perceptual tolerances? So these are the sort of the canonical numbers out of the literature by Steinecke et al. And you can see here, so some numbers here, for example, rotation gains 50% amplification of rotations, 20% dampening, and what we consider these to be is the detection threshold. So as long as you keep your manipulations below this level, people won't be able to perceive it. So as I said, pretty much that was the first obvious question is, well, how much redirection can we apply before it becomes perceptible? The answer is a decent amount. Not a huge amount, but quite a bit. A related question is, how much redirection can we apply before it becomes noticeable to the user? And the answer here is even more. And the reason is the difference of the question of perception is actually a question of is your brain capable of telling the difference? The question of whether you notice is a cognitive issue that can be the result of many other factors. For example, if you're distracted or you're really engaged in a task, you might be capable of perceiving redirection, but you might not notice because there's other things that you're doing. So if you're willing to go above perception thresholds, but you're engaging them in the task, they might not notice. You could probably get away with even more. But these are sort of were the most obvious questions. And when I started doing research in this area, which was about 2009-ish, I wanted to really start asking more interesting, in my mind, more interesting, deeper, and harder to measure questions. I wanted to understand, how does redirection impact the user experience beyond just do you notice or perceive it? Things like, how does it impact your spatial cognition? How does it impact your behavior? How does it influence your ability to perform a task, which is very important if you actually want to use redirected walking in an actual application? So if there's a major theme to much of my work that I'll bring up later on in this talk, it's that many of the studies that I run are, yes, asking the question of do you notice, do you perceive it, but more importantly then going a little bit farther to ask these harder questions that are potentially even more interesting. And then that'll be the first half of the talk. And then for the remainder of the talk, I'll really start talking about more about how we can actually solve some of the engineering challenges if we want to use these redirected walking systems in a real application. All right, so first thing I would like to talk about is a spatial orientation experiment. Now, I already mentioned the impact on spatial cognition. And what I mean by this is I want to know, and there's many ways you can measure spatial cognition, but I wanted to know for this one, basically, how does it impact your orientation in the virtual world? Does it going to confuse you, make it harder to orient yourself? And also, I wanted to know, how does this orient your perception of the real world, like where you think you are in the physical world as well as the virtual? So here's how we measured this. You can see here, we have basically these posts set up on the lab. This was run in about a 30 by 30 foot lab space, so this was a really fun experiment to run because they're basically asked to pick up their display and point to these targets with a tracked controller, and then they put the display back down, and then a graduate student is sprinting across the lab, grabbing the post 30 feet, bringing it to another post, a preordained location within the lab. So it was a very physically demanding experiment to run. So here's what we were measuring. At the beginning of the experience, they were asked to lift up the visor of the display, point at a real target, put the display back down, point at a different target that was also displayed in a post in a virtual world. So see both of these at the very beginning of a trial, and we measure how accurate they are in pointing to the targets. Then all the targets disappear, and they're asked to go through the environment and to the end. During this time, they would be redirected by a total of 90 degrees. Now, for the purposes of this PowerPoint animation, I did the walking and then the rotation separately, just because it was easier to code up. But this happened continuously. By the end of their walkthrough, they had been continuously redirected to a sum total of 90 degrees. Now we asked them, point at where you think that virtual target was. And then one question we wanted to ask is, are you going to point at where that virtual target actually was, where you saw it? Or would you point at its virtual target in its redirected location? Imagine if the target had been redirected along with the virtual world. Are you going to correct for that redirection and point it where it would be? So here's what we found. We measured the error, and so we can quantitatively measure this. So this is angular error, so lower is more accurate. What we see here is that they were for the original position, about 90 degrees off. For the redirected position, correcting for the redirection, they were error about 36 degrees. And if you look at these kind of studies previously in the literature, that's about the angular error you'd expect for pointing at a target. Other tasks that have looked at these types of tests, if you're pointing at a target, that's what you'd expect. So pretty strong evidence that they were pointing to the target in its redirected location. So that's probably to be expected. It's an interesting result, but it's the result I would have hypothesized. The potentially more interesting question is, what happened to that real target? So again, they're redirected by 90 degrees, and they had seen a target in the real world. Were they going to point at where they thought the target physically was in the real world? Or would they have also redirected the target around them? Basically, would the real world reference frame have followed the virtual world's reference frame, and would they be pointing at it after it's in its redirected location? So one way you can frame this question is, how does redirection influence the user's real world orientation? But actually, a more subtle thing we're asking here is, can we maintain both of these spatial reference frames separately at the same time? Now, this was actually a point of some contention. Mark Bullis, who was my mentor, I was doing a postdoc with him at USC, was adamant that people would be able to maintain dual reference frames for both the real and the virtual world. And I was very skeptical about this being possible. It's a very difficult thing to do. So we argued a lot about it, and eventually I was like, I just have to run this study. So here's what we found. Pretty much the same thing as with the real targets. The original position, where it actually was in the real world, about 90 degrees. A little bit more error, but not statistically significant compared to the virtual targets, about 45 degrees error for the redirected position. So pretty strong evidence that in this case, they were basically the real world was going along for the ride with redirection. They couldn't maintain two reference frames. And so basically your real world reference frame was subject to the manipulations that we apply in the real world. In the virtual world. So this was a really, really interesting and fun result, and I got to go to Mark and say, look, the data backs me up, and that settled that argument. So that was a really interesting study. And now I'm going to shift gears a little bit, and I'm going to, are there any questions about this study before I move to the next one? Okay. I'm going to move next to a couple other illusions that I started to get interested in. I was doing work in redirected walking, and I was like, well, these motion illusions are just one mechanism that we can exploit. But there are plenty of other possible ways in which if space is so malleable and people, maybe there's other illusions that we can employ to achieve the same goal. And so the first one I'm going to talk about, and I know a couple of you in the room are familiar with this already, is a phenomenon known as change blindness. And to illustrate this, is a very well-known phenomenon in the field of psychology. I'm going to show you a picture. Basically, take a look at this picture, and then I'm going to show you another picture in a second. I'm going to ask you to see what's changed. For those of you who haven't seen this example, feel free to call it out. Does anyone who hasn't seen this example notice what's changed in this image? Okay, I'm going to make it real easy for you now. Okay, so why was that hard? It was hard because I flashed an interstimulus image, even for a split second, and that disrupted the motion that you saw. And it turns out that the human visual system is very sensitive to motion. That's what we use to detect updates to a visual scene. So if I flash an interstimulus image, or in VR, if I do something behind your back and not directly in your field of view, you're very, very, very difficult to see that subtle changes have occurred. Been replicated many, many times in different psychology experiments, but at this point, no one had ever actually tried using this in VR for the purposes of redirection. So how do we do that? So here's a quick little animated example of the test environment that I came up with. So in this one, there's a series of hallways. It's a whole office building with 12 rooms. And each time you walk into an office, you go inside, you walk inside the room, walk up into basically a virtual desk. We gave them a task just to turn on a computer and look at an image on a computer, just as a way to get them to walk through the environment. While you're looking at the computer, watch what happens to the door behind them. So basically what happened there is that the door swapped 90 degrees in the corner of the same wall, and then the entire hallway and everything outside the room gets adjusted by 90 degrees. So you go out, you continue down the hallway, you make a left, you go to the next room, essentially, and you can basically repeat this an infinite number of times. As long as you're going from room to room, you can just do this behind their back every single time. Important thing is that when they're looking forward, everything in the room is visually consistent, and all the changes occur behind their back, outside of their field of view. So this is just a quick example of it actually running. So this was the test environment you can see. Sorry about the frame judder there. I think it's just a old video on probably an old codec. Didn't actually occur that in the VR environment. But you can see here the same thing is occurring. They're walking to the computers and basically going through this whole very large office building. So there's the entire office building. So we ran the 77 people through this experiment. Actually, 2 different experiments on this. And we went through a battery of measures trying to find out, well, first we asked them just if you noticed, but then a lot of other measures that just tried to get at, in very subtle ways, did you notice that anything was changing in the environment and stuff like that. And really, I was astonished in both of these experiments that out of all of us, only one person was able to actually identify that the door had changed, or even that something in the environment had been altered. So what does this tell us? One, it tells us that there's always one weirdo in every experiment who ruins your perfect record. And then 2, it tells us that this is a very powerful illusion. That with that level of repeatability, it's very, very compelling. But again, I wanted to look at these harder questions beyond just do you notice. So one of the ways in which I decided to do that was to give them sketch maps. So I asked them to sketch out the environment. And it's actually not possible to represent this environment in a 2D sketch. It's dynamically changing. You'd have to draw 12 different sketches or more to be able to do all the different variations. But overwhelmingly, the sketch maps that we looked at, that we received from participants, looked like this. So clearly they were perceiving the structure of the environment that we had intended them to, despite the fact that it was dynamically changing. And of course, we had these quantitatively evaluated by independent graders and measured appropriately and ran statistical tests. They were rated very high in terms of their matching to the original environments. So I just like to show the image and say, yeah, we can just look at those and say that these are very representative of what we received overall. So again, evidence this is a pretty powerful illusion, but it's also an illusion that could really be employed in an environment without messing up your learning of the structure of the environment. It also has some cool advantages. Here's an example of a demo environment I put together for the US Army, where we actually trucked 1,000 pounds of gravel into the lab to build a 30-foot long gravel roadway. So side note, not the smartest idea I've ever had. We were cleaning up after it for about 5 years. So when I moved to the University of Minnesota, I promised them I wouldn't attempt this. But there's some interesting advantages here. One advantage is you can actually walk out, and I'm going to pause this video here for a moment. You can actually walk on it and feel the vibration, the crunch of the gravel under your feet. You get a haptic sensation from it that really qualitatively, you can watch people do this. The moment they do that, you can just see like they're buying into this experience. It's very powerful when you can incorporate physical feedback into a VR experience. But because this is a discrete, predictable change, unlike these continuous redirected walking techniques, we can actually align them in the right way to the same haptic object. So watch what happens. Whoops, I'm skipping ahead there, stealing my own thunder. Okay, so I'm going to skip right here to this. Okay, so as I walk here towards this room, and they were searching, this was a search test, so they're going to search through this room for these boxes. And let me press the play button. And of course, PowerPoint doesn't want to play the video, so we are probably, well, what you would see if PowerPoint wasn't deciding that the video was going to give me the infinite spinny wheel is that essentially the room would move. There would be a double whammy of change blindness illusions. A room would move here, a room would move here, and essentially what you'd get is an exit for the room building that you entered would move 30 feet down. So every time you exited that building, you'd then continue walking along the path, and then you would essentially be able to reuse that 30-foot walkway, turn it into an infinitely long roadway, and every time you do it, you get the physical feedback. So it was a really cool illusion and a benefit of using these types of techniques over regular redirected walking. And there's the wonderful, powerful crash. So just let me bring that back up 1 second. Okay, so next I'd like to talk about the next illusion. The change blindness stuff was such a powerful technique that it really got me thinking in the follow-up to this work, well, what are the other ways in which I can, if people's learning about the space is so malleable, how else can I exploit this? And I like to give credit, the first one was credit to me getting involved in with site collaborators. The second one was just because I'm a sci-fi nerd. So who here is familiar with the BBC television show Doctor Who? Okay, a couple people. So for those who are unfamiliar, this is a show where the Doctor, who's an alien, flies through time and space through a time machine called the TARDIS, and when you open up that small box there, you open it up and it's actually incredibly expansively large environment. So there's always this moment when he brings new companions in the show where they open it up and they go, it's bigger on the inside, and becomes kind of a trope in the show. And it always seems so magical to me, and I wanted to know, what does this feel like? What does it feel like to walk into something that's bigger on the inside? Well, luckily I'm a VR researcher, so I can build that. So here's the test environment that I built to look at these impossible space illusions. So similar thing, it's an office type environment. They walk to a desk, then we just do that to get them to walk to the inside the room a bit. They leave, and then as they're walking down a hallway, what we do is essentially as they're halfway down the hallway, we delete the first room and add the second room, in overlapping a good amount of space with the original room. And then they walk to that computer and turn it on. So basically, if we overlay both of these rooms on top of each other, they're coexisting in the same physical space, so both of these rooms are essentially bigger on the inside. Okay, so the fact that they are spatially overlapping and we can measure the quantitative overlap gives us a nice quantitative measurement that I can actually manipulate how much overlap between these two rooms exist, and then I can sort of try to quantify the level of impossibility that users could tolerate or before they would begin to notice. So here's how we did this. So I gave them a 2 alternative choice task for each room. So each series of rooms, they did many, many trials at different levels of overlap. And each one, they went through that trial I just told you, and then they answered, they were asked, is this an impossible or possible space? They were explained all of this beforehand, so they knew what these illusions were. This one's one where I explained the illusion to them. They knew exactly what it was. And they just had to tell, is this impossible or possible? And then what we essentially do there is, over all these trials, we compute the pooled probability of responses, and they don't have a neutral option. And because of that, we can just look at the 50-50 chance level as basically being like the level of which you're no better than flipping a coin. And so what we do is we then fit a function to this data, and what we look for is, again, that 50% level. How much are they, that's the point at which they became able to reliably detect the illusion. And what we found looking at this, and so you can see these are the probability of responses from 0 to 1. So just percentage of being able to detect impossible for each level of overlap. 0, so that's perfectly possible, all the way up to 75%, which is a huge amount of overlap. Most people could tell at that point. And what we found is that it was about 56% overlap before people could reliably tell that this is an impossible space. So that's pretty cool. If you think about that, if you're a VR designer and you're designing interior buildings, you immediately can say, well, if I have these adjacent rooms, I can make them 50% larger and people won't really be able to tell. And this is when they're actually really trying to. That's a lot of space savings and real estate, virtual real estate, that I've reclaimed in my VR environment. But again, I wanted to ask some harder questions. So let's beyond just how much did they notice it. So for this, I designed a distance estimation task, and this is sort of stealing an empirical methodology that's very extensively used in VR and in psychology called blind walking. And what we actually wanted to do was see how would they behave, how would they perceive distance in this environment. So what happens is when they get to that second room, they were asked to point towards the wall and imagine where they were standing when they turned on that first computer in that first room. Then,
are these the people who know the illusion already?
Yes,
okay.
All of them know, same experiment, so they all knew. So then the display goes dark, and they're asked to basically stop and walk until they're standing on the point that they were physically standing. That's important instruction, where they were physically standing when they turned on that first computer. Of course, in the case of a lot of overlap, that point would not be through the wall, and in cases, many points, time in 75% overlap, it was only like 2 steps away from when they were physically standing. So we wanted to see whether they would stop to where they actually were physically standing, or if they would continue to walk, essentially correct for the compression of the environment and walk an exaggerated amount as if the two environments, the rooms had been separated out. So here's what we found. So this is actually just guide data. So what you're seeing here is, again, overlap level on the horizontal axis. On the vertical axis, this is walked distance as a percentage of what the actual distance accurately was. So if they were accurate to where they were physically standing, we'd expect their data to follow this horizontal guideline here. This is what it would actually be. If they were correcting for that compression and walking as if they were separated, we would expect them to follow this guideline right here. And so this is what we ended up finding across 2 different room conditions of rooms and sizes. And I love this. This is one of the coolest results I've ever done in studies, because I don't need statistics to tell you which of these 2 use cases they actually did. I think you can just look at this and say, okay, they were pretty clearly correcting for this compression. And the really neat thing about this was they were doing it even when they noticed. In the 75% overlap condition, they were responding like a 90% of the time, I know this is an impossible space. Yet they still behaved and were performing as though the real world rules still applied. And I think this is a theme that I'm seeing in a lot of my work, is that even when people notice, it may not be that big of a deal as long as they're comfortable, because people are tuned to being able to operate in the real world, and the real world rules still transfer. So this was one of those study results that I just love to bring up, because it's just, there's so much going on here. So we tried a bit to think about how we can generalize these illusions, and this gets at the dynamic content generation theme of XR Advance. So what you're seeing here is a procedurally generated environment where all the rooms are pre-modeled, but all the corridors are not. And what essentially you do here is the system is pre-calculating how much space exists, and then is generating a series of twisty hallways. These are basically impossible space illusions that basically, when you exit a room, it calculates how much space I have and generates a twisty hallway that goes back in on itself and then gets you to the next room. And so this is a really flexible, we call this flexible spaces. We modeled this as sort of like a virtual museum, and we think it could be really useful in use cases where the spatial layout of the rooms doesn't matter so much as the content that you're exploring. For example, wouldn't be probably the most appropriate thing for a tactical 3D shooter game, but for a virtual museum or educational experience where you want to walk through comfortably and you want to get to the next exhibit to learn, then it doesn't really matter what the layout of the corridors are. Generate a twisty hallway that loops back in on itself, and then you won't have to use all of these uncomfortable locomotion techniques. So to summarize, wrapping up this portion of the talk, in this work, we measured some interesting things about redirected walking and spatial orientation, but we also introduced a new class of spatial manipulation techniques. And in the course of this work, I actually developed an expanded taxonomy for redirected walking that is more encompassing of different types of illusions. That is currently the standard taxonomy used today. And if you're interested in these impossible spaces illusions, this has made its way into a commercial implementation. There's an experience called Unseen Diplomacy on Steam VR that makes use of this impossible space illusions I just showed you. So at this point, I'd like to shift gears a bit and then move on to the last portion, which is engineering redirected walking systems. Everything up till now was about sort of the theory of redirected walking. Does it work perceptually? But what if we actually want to put these into practice? And I'm going to put this video up that I showed you earlier. This is very similar. So this is the one for SIGGRAPH. And if you were to nail me on anything, I was like, oh, great, look, we put the couch in here. It's a really small confined space. But if you wanted to be critical, you'd say, well, yeah, you made it work in a confined space because it was a scripted experience that you're following this zigzag path, which is the similar zigzag path that the original UNC researchers did. What if you go off script? What if you decide to walk back and forth between these exhibits in a different order? Well, you'd say, well, at that point, you'd hit a wall. This would break down. So this worked really well for a scripted experience. What happens when we give the user freedom? Well, turns out that there is a way to handle these sort of collision cases. If you're going to walk outside and you're going to hit a wall, we do what's called a reorientation event or reset. And so what you do is, essentially, when you calculate that you're about to hit a collision with something, what you do is you stop the user, and then you can introduce some sort of intervention, oftentimes a distractor or something like that, that gets them to turn around. During this turn, we can introduce rotation gain and physically reorient them away from the physical obstacle so that then when they continue forward in the direction they wanted to go in the virtual environment, they are now pointing directly away from whatever they were about to hit. So these are our fail-safe events in the virtual environment that we use when redirection walking detects that it's not going to be able to prevent a collision. So obviously, one obvious thing that you might say is, well, these sound like you don't want to interrupt the user too much. This sounds pretty jarring. One thing that we explored was the idea of context-sensitive reorientation. So this is an example where, and I'm going to try pausing this without PowerPoint crashing. What you're essentially seeing here is it popped, this was a virtual scouting task for the US Army. It popped up a panoramic photo prompt. So when it detects you're about to collide with something in the virtual world, you're said, oh, use your handheld smartphone to take a panoramic photo. And it fills the meter like you would be with your taking a panoramic photo. And by the way, when you're done, by the way, we've also reoriented you away from the obstacle you were about to face. So this is an idea about seamlessly building it into the narrative of the environment. That's obviously not generalizable to other tasks, but it's meant as a sort of like an inspirational example of how one could build a task around these sort of reorientation events. So one of the things that one of my first PhD students, Mehdi Asmandian, who has since graduated, tried to do in his PhD thesis was try to really understand what are all the components of a redirected walking system. Turns out there's a lot going on here from an engineering perspective. There are all these spatial inputs in terms of the physical space, the virtual environment, the user's pose, basically how much redirection has been applied before. And then there's all these sort of like user input variables. What are their individual detection thresholds? We don't want to exceed them. What are their preferences for reorientation? And then all of this has to be input into the system. You have to have internally some sort of heuristic or algorithm that's applying redirection and reorientation. You need to do some sort of gain smoothing because you don't want to like re-ramping things up too much if you're changing things. And you need to know sort of everything that's going on in the state history. So all of these are components of a redirected strategy. And then out of that algorithm, basically a controller then determines each frame, translation gain, rotation gain, curvature gain. Again, these are the three motion primitives for redirected walking that I talked about earlier. Spits those out every frame. How much are we redirecting the user? Hopefully that's occurring at 90 frames per second. So when we're going through this, the question then is, if we're going to compare all these redirected walking algorithms, what is our performance metric? How do we measure how good a redirection algorithm is? Well, the way we came up with, and this other people in the community have used this metric as well, is basically many times do we need to reset you? The ratio between how far you can walk in the virtual world and the reset count tells us basically how effective was this redirection algorithm. The better algorithms will prevent resets, and so this ratio will be higher. So that's our performance metric that I'll basically look at, or in the context of traveling the same virtual distance, just raw reset count, minimizing that in experiments is what we look for. So the question of now of building a VR system and how we would engineer this comes down to how much can we predict the user. So on the spectrum of freedom from complete freedom to absolute freedom, well, the best case for redirection is going to be a linear route, like I showed before. There's a class of approaches that I'll talk about called static planning. If we have branching pathways, there's some sort of structure in the environment. For example, interior office buildings may not be linear, but there are hallways and corridors and things like that. There's a structure. We can use approaches known as dynamic planning. And if we have a completely open world, that's actually the worst case scenario for redirected walking. We basically have to use what's called reactive algorithms, which are greedy approaches. We've done work in all three of these categories that I'll briefly touch on. Let's start with the worst case scenario for redirected walking, reactive algorithms. Open worlds, we can't predict the user, they have absolute and complete freedom. Previous state of the art in this, there are two general approaches that were proposed, steer to center and steer to orbit. What happens here is the X marks the location that the redirection controller is basically always trying to steer the user towards. So there's no prediction here. It's a greedy algorithm. It's naively just deciding what's the direction to that target, steer them there. In steer to orbit here, it's actually steering in orbit around the center. So it calculates a radius and then tries to steer them to a point that always gets them to orbit around the center. So people have looked at this before. They work to some degree. They're not that great. They need a lot of space. They'll work great if you have a lot of space, but tend to break down. If you have a smaller space, or more importantly, if you're in the wild, which is something I'm really concerned about now, operating in real world situations, what if you have an obstacle? Well, steer to center is going to steer you towards the center always. What if there's an obstacle between you and the center? Steer to orbit, what if there's an obstacle around the orbit, or a non-convex boundary, or an irregularly shaped space? What is the center of an irregularly shaped space? So these are known problems, and these reactive algorithms really tend to break down in these cases. So to try and solve some of these problems, or begin to address some of these problems, we took inspiration from the field of coordinated multi-robotics, who have actually been thinking about these sort of path planning and complex spaces things for a long time in the context of robot navigation. And so this is actually very recent work that we just published last month at IEEE VR. And the new algorithm we came up with is called P2R, or push-pull reactive. And so the basic way this works is, given a physical environment, we can calculate an artificial potential function. And the way an artificial potential function works is it's basically a function, an n-dimensional function that is a measurement of an abstract energy of the system. And essentially what you want to do is basically be in the lowest energy state here. So if we can, the way that we construct the artificial potential function here is based on the geometry of the physical environment, and then we can use something like gradient descent to always push you towards favorable locations. We called it push-pull reactive. Well, actually, here, I'll show you this first. From that artificial potential function, we can actually calculate a gradient field. So any portion in the physical space, we can calculate the favorable direction along that function for the user to be in. And this really depends on the geometry. But if you calculate this gradient field, this allows us to essentially push you away from obstacles and pull you towards favorable locations. So this is why we called it push-pull reactive, or P2R.
5 minutes.
Okay, thank you. So for this, just very quickly to zoom through some results here, basically what we did is compared this to steer to center, which is the previous state of the art, and we found it's always better. It's never worse in any of the environments we tested. This is reset count, so lower is better. So we tried it with multiple different physical spaces. So basically P2R outperforms and is these previous algorithms and can handle some of these complex physical space things. All right, I'm going to speed through the dynamic planning really quickly. I just want to quickly talk about how we model prediction. So given a structure of the environment, we can either say, for example, in this hallway example, a user might be able to go forward, go left, turn, go left or right, go backwards, turn left or right. That's looking to me a little bit like a graph. So we can model for physical spaces, we can model a prediction graph of where users will be likely to go because they're not going to walk through walls. And if we have a prediction graph, we can then input that to the system and not use those reactive algorithms. And there are two dynamic planning predictive algorithms that use these prediction graphs that have been previously proposed in the literature. But what we want to do is minimize the deployment overhead because these prediction graphs need to be prepared manually. So that's going to be a problem in dynamic environments. So our work here was to try and get that deployment overhead down by generating the prediction graph automatically. So here's how we do it. We essentially divide the space into convex triangles. We essentially look at the connectivity between these polygons. So these polygons are all fit to the walkable space. And then we're able to basically generate that graph. And we were able to do it using navigation meshes, which are a tool already built into game engines like Unity. And so this is an example very quickly of our algorithm, which is generating these prediction graphs in real time. So that helps us use these dynamic planning algorithms. And then finally, very quickly, what happens if we have these static planning situations where there's a portion of the route that's linear? Well, one of the ways we can do this is essentially use combinatorial optimization. In this example, if we go 90 degrees, left turn, and then walk, based on where we apply redirection, we can have the user end up in all of these possible locations by just manipulating the gains. So what if we just exhaustively compute all possibilities and then pick the best one that minimizes resets? Well, the problem is the branch factor here is super high, so you very quickly end up with an intractable problem due to combinatorial explosion. So my PhD student, Maddie Asmandian, figured out how to basically discretize this space in a very clever way. I am not a combinatorial optimization expert, but basically by managing that explosion, he was able to do this and compute it in an efficient way. The next question is just, let's keep the user on the path. These micro adjustments in the path as they're walking through the world, this is just some real user data. Even after about 3 turns, they tend to get off the path and then you can't project them in forward and your combinatorial sort of approach to prediction breaks down. So Madi also came up with a way to basically inject micro corrections into redirection to steer them back off on the path. So we're not only redirecting away from obstacles, but redirecting them to stay on the path we predicted, allowing our predictions. Essentially, every time you get to a turn, it gets you back on the path. So putting this all together then, we can plan out these routes to explore very large environments. This is actually the warehouse space we used to have in our old building, and then map that to a optimal, exhaustively optimal redirection approach within whatever space you have. And it works. So this is an example that we did with a real estate company where we planned to walk through of an actual warehouse, a model of a space that they had prepared, not by an artist, as you can see, programmer art, but allowing you to explore the entire thing using real walking within our tracking space. And then really quick, just to give you a sense of how good this can be if you have a linear route or a portion of an experience that has a linear route. This is sort of like reset count with different algorithms. This is with no redirection, so you're just resetting every time you hit a boundary. This is tracked space size, so these are bigger tracker spaces. This is with reactive, steer to center, so that's the greedy algorithms. Not great, a little bit better. These are with those force, which is a dynamic planning algorithm. So a lot of better performance if you get prediction. But this is with copper, which is the algorithm that Maddie did, the combinatorial optimization approach. And the interesting thing here is, notice for the test that we ran, at about 10 meters you hit a magic sweet spot where you basically stop encountering resets entirely. So at about 10 meters wide of a square space, you can essentially apply this approach for a linear route and completely avoid resets. And that might sound like a really big space, but I would point to the fact that we have these inside-out tracking headsets where now all the headsets are doing the tracking on board and spatially mapping the environment. And if we have that, then we can really move these out into the world into ad hoc spaces. The atrium of this building, for example, was pointed out. There's a lot of space in there. It's a complex space. There are obstacles and things you need to deal with, but the amount of space is big enough that we could employ these algorithms and get around. If we can solve the problem of obstacle avoidance, you could redirect your walking to great effect. And then is it okay if I just take 1 or 2 minutes over? Okay. So I'm just going to quickly point to a couple areas of future work and then close. One area, again, is dealing with these walking in cluttered spaces problem. This is far from a solved issue, but this is just a quick example of some of the work that we started to do. These are work of my students at USC before I moved. And what they're doing here is we put up obstacles, and you're going to see the red thing, rectangle there is a moving cart. So she's going to push the moving cart, and it's going to trigger a replan. So always in the background, this combinatorial optimization algorithm is measuring the physical environment and saying, oh, the environment's changed, trigger a reset. We do it in a second or two, update the plan, and then we can continue redirecting. So this is moving towards the idea that we're going to sense physical spaces and be able to navigate you around clutter. So to summarize, the virtual laws of physics are surprisingly malleable, and what we've seen from many studies, not just the ones I've done, is that human perception will adapt and recalibrate and is pretty robust. We can exploit this fact to transcend the limitations of the real world. And I say transcend here because one of the things early on in VR, I think people were talking about was recreating the real world. But I think we can actually use this to go beyond what we can do in the real world, experience impossible spaces and change blindness illusions. And I like to say that virtual reality is the closest we'll ever get in our lifetimes to experiencing real magic. For those who are interested in redirected walking and trying out some of the basic illusions, we actually have on GitHub an open source toolkit called the Redirected Walking Toolkit that you can download. It's free for commercial and non-commercial use, and it works with Unity. So quickly highlighting a couple research directions. I always get asked about this, multi-user redirection. So if it works for one user, can you make it work for 2 users? The answer is yes. Although it's more complicated and spatial concerns are important. Predicting collisions not only with objects but also other people. We've done one paper in this area, and Eric Hodgson from Miami University has done a couple as well, but it's very much an open area of work. I won't talk about the specific results we did, so I'll just skip through that. Another question is individual differences and adaptation. So we've done some work very recently last year where we started to look at, well, are these one-size-catch-all perceptual thresholds really good enough? Because there's so much variance in simulators and sickness symptoms and sensitivity to redirection. So we try to come up with an adaptive procedure that can calculate an individual's gain. And what we found here is actually there's an interesting effect. We were able to find one that was very efficiently able to calculate an individual gain, but we tested another procedure which used a staircase procedure and gradually ramped up the gains. And we found is people tend to get much higher tolerances to redirection as we gradually increase. So this warrants future study, but there's definitely some evidence here that supports the fact that there might be an adaptation effect that users experience if you're doing this over and over. They might be adapting to this, and you might be able to redirect them more. But what is that doing to them if you're changing your perception? So these are important questions, I think, for future study. So last slide. In general, I would point to the fact that along the mixed reality continuum from a physical environment, AR is traditionally viewed as something that is mostly physical, but has virtual elements. That's moving towards the center of this spectrum. AR is getting much more immersive. VR is typically viewed as being something that's purely virtual and doesn't account for the physical. That's also moving towards the center. And as it gains more sense about the physical space around you. So ultimately, I think these two are convergent, and AR and VR all kind of go together in these systems that need to be sensitive to the physical world and allow you to locomote and operate within them. And with that, I would just like to acknowledge all of the PhD students, postdoc Timothy Gretchkin, engineers at ICT, and collaborators David Crum and Mark Bolus, who worked on me throughout the course of this work. And with that, I know I'm 4 minutes over time, but hopefully I have a couple minutes to answer questions. Thanks.
Thank you. We have time for questions, right?
Yeah.
I have a couple questions.
Sure.
One is, so I have a question and a comment. My question is about one of the earlier studies you presented where you're asking participants if they could keep track, you were evaluating whether they could keep track of a location in the virtual world and in the real world. And that really what they kept track of was the virtual locations in all cases. With modern VR, we're often reminded about the real environment as we approach a boundary. The little chaperone walls pop up and stuff. How does that affect our, immersion in the virtual world versus the physical world, and does that change the balance between them?
Yeah, so I think first of all, the fact that we have to use these chaperones to remind people is evidence of how hard it is to keep track of your orientation in the real world. It's something that is actually really challenging. So we need to build tools that allow people to do that. I think to get more at your specific question, I think my personal experience has been that chaperones are a necessary evil in many cases. They are jarring, and I think that they, by nature of the fact that they are sort of forcing you to do this dual reference frame awareness, which is very, very difficult, it does diminish the VR experience. And I think that's a fairly uncontroversial statement to say that they do diminish the VR experience, but colliding with a wall will diminish your experience more, so it's a necessary evil, if that answers your question.
Yeah, thank you. I'll hold on to my comment and see if there are other questions. But.
Yeah.
I'm not familiar with like the dynamic planning for the redirected walking, but are you using any user behaviors to predict where they might choose to walk? Is it like I'm not sure, using like eye gaze or
yeah, great question.
Where sort of they're walking towards, are they making a left or right?
Yeah, fantastic question. So in the context of the predictive algorithms that I showed you, no. When they talk about predictions and prediction graph, they're talking about how predictable is the user's behavior based upon the structure of the virtual environment they're exploring. What your idea, though, about using things like eye gaze and sort of like more of the signals that are user-specific and measured from their behavior is a fantastic one. I think there's been a couple papers that have at least looked at like trying to predict locomotion from eye gaze, but it's a really sort of a new area. And certainly redirected walking algorithms would benefit tremendously. All of the different approaches would benefit tremendously from real-time prediction, because then we can preemptively apply redirection before an obstacle is encountered.
So on the thing with the room 75% overlap, it seems like the sort of disperception's happening as they walk along the hall.
Yep.
Like that's when they get sort of screwed up.
Yep.
So walking down in a pretty innocuous hall would be easy to do. So I wonder if it'd be worth trying with a less innocuous hall or on railroad ties or.
Yeah. So let me tell you a little bit more about my anecdotal observations during this experiment. You are right, the innocuous hall is extremely hard to do. So what participants started to do was start to give themselves cues like what you're talking about. So the two most biggest strategies they were using were counting steps. So they started doing this, trying to game the system. And then the other one was standing in the threshold of the doorway and going like this, looking down the hallway and in the room and being like, does this make sense? Does this make sense? And I didn't stop that behavior because I figured, well, okay, they're trying legitimately. So if anything, these numbers are going to be conservative for how much we can actually do, expand these spaces because they're using these strategies. And if they were not incentivized to do it, we'd probably be able to do way more. To your point, yes, it's a great point. But at least in our experiment, the participants were trying to do that themselves using clever strategies.
One comment I have is, I have one other question, but a quick comment. I like how your work so nicely integrates spatial cognitive theory, and I'd argue that in some cases it seems like your work actually predicts some theories in spatial cognition. Like, I don't know if you follow Bill Warren's work, but he does this spatial cognitive work on where people kind of travel through virtual wormholes, and he's arguing that people don't really have a cognitive map in the Euclidean sense. And really that's what you were demonstrating in your paper with the impossible spaces where they're able to draw a map, sure, but they're also able to navigate this impossible space and they're not troubled by it at all, right? Which kind of suggests something about what they're actually holding in their head. And so I just think that's really nice. But the other question I had was going back to this question about the hallways. I think it's interesting that many of at some level of disagreement between the physical and virtual space, people were able to notice reliably that there was this disagreement, and yet in their walking responses, they still walk exactly to the virtual place that you would predict they would walk. So it's like they know there's this illusion that they're falling victim to, and yet they can't help but walk to the illusory location. I think that's really a surprise, and I wondered if you might find that people who are more affected by the illusion will walk to a different location than those who are less affected by the illusion.
Yeah. So I haven't specifically done any studies that have attempted to measure that phenomena in the way you're describing, but having done hundreds of people through both, formal experiments as well as many hundreds through demos and other experiences over the course of the last 8 years, what I can really say based on observations is I've never experienced any person who noticed the illusion and then said something negative about it, specific to the change, blindness, and possible spaces work. If anything, it seems magical, and if they can figure it out, they're all proud of themselves, and then they just seem amused by it. Whereas redirected walking, I think, is a different thing because there's user comfort, in exceeding detection thresholds. So my sense is that as long as they're employed in a way that doesn't interfere with the ability to perform a task, right? They're employed in a way that's subtle and allows them to still perform the task that they're willing to perform. I really can't see a downside to their use, and I can't see that the effects that they have, even if you notice, are that there are any negative effects to using these. Like, I think if you did this in a really jarring way, like you could design an environment that is completely unpredictable and impossible to navigate by overusing these techniques, then I could see it interfering. But in the way that we're thinking about using them to maximize walking, I have not yet encountered any people who have given me the sense that that would be a problem.
All right, we should wrap up. Thank you.
Thank you.